Okay, so the last diagram, that phase diagram that we're going to look at is called a pressure composition diagram. Sometimes referred to as a PX, X meaning oil composition, or PZ more correctly, representing some total composition. And the diagram is typically used in understanding gas injection, the effect of injecting gas on oil recovery. And what's usually referred to as enhanced oil recovery, EOR. At least it's one of the methods of enhanced oil recovery. So we'll look at the diagram itself and then try to understand it in light of its application. So what we're going to start with is some kind of a reservoir oil. Which, let's say that the initial composition, it's an oil composition. We're calling it oil by some label. And we're going to inject and we're going to inject some gas. That gas is, I'll just refer to it as injection gas, IG, injection gas. It might be something like pure CO2 is very popular to look at least to evaluate. Could be something that's essentially pure methane or plus smaller amounts of C2 to C4. This is what we refer to as a lean injection gas, or lean hydrocarbon gas, I guess you could call it. You might have something that's got primarily methane and heaviers. This would be typically like just a separator gas that you get off of a primary separation. At the surface, you take whatever you're producing out of the reservoir to the surface. You put it through a vessel, a container, at low pressure and temperature, 100 bar, 10 bar, something like that. And you get gas coming out of the top and oil going out the bottom. The gas that comes out of the separator will be our primary first stage separator gas. And that might be treated or not treated. You might or might not add some intermediate components, C2 to C4, to create an enriched gas. So basically you've got lean gas, separator gas, or some gas that's been enriched with artificial amounts of ethane through propane and butane. You might use CO2. And actually, when I first came to Norway, came looking to do research on nitrogen injection into North Sea oil fields because the oil is very light and nitrogen is readily accessible, and it ends up that the Equilibria field, which is about 6 billion barrels, I think it's the number 2 or 3 in Norway, before they did water injection successfully, before the pilot proved a successful water injection pilot, in the early 90s, we were looking at late 80s, early 90s, we were looking at, well, the operators were looking at injecting nitrogen into the Equilibria field as an enhanced oil recovery method. I say we because we were contracted to do some of that experimental and modeling work with nitrogen interacting with oil. So you've got, these are basically the types of injection gases that you might look at. And so what's done is that you basically take the reservoir oil, you add a certain amount of injection gas, you bring it to equilibrium, you find its saturation pressure, bubble point, or maybe dew point. Maybe you measure as a function of pressure how the volumes change. You add another injection gas amount, you do the same kind of measurement of what's the new saturation pressure, how does the volume change with pressure, and you do that maybe 4 to 6 or 7 times. Additions of anywhere from 4 to 6 additions of injection gas. So what that leads to is a diagram that kind of summarizes what you find. It's typically a plot of mole percent injection gas. So out here we'd have 100%. Here we basically have our original reservoir oil. Here we have pure injection gas. And the pressure is shown here, and we're at a constant reservoir temperature. The original bubble point might be there. We add some gas, maybe this much gas, and we get a new bubble point. And so typically this curve is going to look something like this. Where this, this point here might be a bubble points. So I'll make these green as I've been to be consistent. Bubble points. And then dew points. Something like that. And we may or may not know exactly where it transitions from bubble point to dew point, but let's just for the sake of argument say that we have that point here, which would be a critical point. Unfortunately, that's right at the maximum, which I don't want it to be because it doesn't necessarily have to be at the maximum. So I'm going to change this a little bit and make the critical point here and put another dew point here, something like that. Okay. And basically everywhere below this we have two phases. And if you're injecting CO2, carbon dioxide, you may actually have some of the region with three phases. Okay? If you're injecting CO2 or an enriched gas. So what I'll say here is that you might have some, typically it's local, but regions with three phases. And those three phases would be kind of a, for example, could be a CO2 rich gas phase, a CO2 rich liquid phase, and a hydrocarbon rich liquid phase. So you've got liquid 1, liquid 2, and vapor. So they would call this typically liquid 1, liquid 2, vapor, three-phase situation. And there might be just a small range of pressures and compositions where you see the three phases. But so we've got in this region here two phases, and then above the diagram out here we've got single phase. So this kind of satisfies the criteria of a phase diagram. It's a map of where you have two phases, where you have a single phase. I'll make just one comment on this diagram, that the maximum here We don't call it the Criconden bar. This maximum pressure is equal to the, well, okay, before I tell you what it's referred to as. Does anybody here not know what miscibility means? And there's nothing embarrassing about it, but does anybody not know what miscibility implies? Okay? Because if you don't put your hand up, I may point to you and say, okay, you know. All right? Raise your hand if you don't feel like you know what it is. And it's fair. It's not like, okay. It's not one of the standard chemistry concepts that we deal with. But miscibility is a very simple concept. You've got a mixture A and a mixture B of anything. Single phase, each mixture. Just for the sake of making it easy to understand, we've got diesel and gasoline. Everybody sees that at the gas station. Diesel and gasoline. Single phase, you put them in a tank, single phase at 1 atmosphere. If we mix together those two mixtures in any proportion, 99% diesel, 1% gasoline, 99% gasoline, 1% diesel, 50-50, 75-25, it doesn't matter. If any mixture, the resulting total mixture is still single phase. If it remains single phase, then A and B are considered miscible, directly miscible. Okay? And it's a concept that's very important. Well, the miscibility concept is an important concept in looking at gas injection into oil reservoirs. Now, we never inject something that is directly miscible with the oil, or almost never. Okay? Because that would be a very expensive injectant, typically. Okay? Or a very high pressure. But this pressure here, P max, that's the lowest pressure where the injection gas is directly, and I have to put this term directly, I could just say miscible, but directly miscible, meaning we just mix the two. Directly miscible sometimes this directly is referred to as first contact. Okay? That means if the gas goes into the oil reservoir in any proportion and hits the oil in any proportion, it's miscible. That's called first contact or direct. So it's the lowest pressure where the injection gas is directly or first contact miscible with the reservoir oil. Okay? Other words called, this is the minimum first contact miscibility pressure. I'll write it MMP for minimum miscibility pressure, first contact, subscript. Okay? That is defined by this pressure composition diagram. Okay? So if you happen to be able to inject at that pressure or above, wherever that injection gas slides through the oil reservoir, it's going to recover 100% of the oil, 100%. Wherever that gas moves in the reservoir, it's going to clean it out completely. 100% recovery. Nothing's going to be left in the pores but the injectant. That sounds good. Now, it ends up that you often can inject IG into reservoir oil at a much lower pressure and still develop miscibility. But that's a very complicated phenomenon going on. It's a very, we're not going to go into it, but chapter 8 in the monograph, if you're real interested in that, chapter 8 discusses in detail how that can be. Okay? How can you develop 100% recovery, miscibility, at a pressure much lower than this MMP first contact? It might even be lower than the bubble point pressure. So it's an important and it's an interesting thing, but it's kind of outside the scope of this course. All right? So that's the pressure composition diagram, and I think at this point, I'm hoping there's some questions out there about all this stuff we've been talking about. I mean, maybe you haven't had enough time to digest it, but is there any questions out there just floating? Yeah.
For example, the miscibility you have talked about now. For example, if we have taken a sample from the reservoir that was at its initial composition, and we have determined this P maximum of this minimum miscibility pressure for that one, and we are going to inject the gas at this pressure so that it can have first contact miscibility.
Right.
So when we will inject the gas and we will produce the oil, and we are not maintaining the pressure 100%, so there will be some pressure drop in the reservoir and the oil composition will change. So this definition of minimum miscibility pressure will not remain same throughout the reservoir life.
Well, the question is, when you inject into the reservoir, if this is your injector, and then this is your producer over here, and I'm going to plot pressure, okay? Well, typically, if it's vertical wells, then you have a large pressure gradient. It goes something like that, and then this becomes fairly flat, and that through most of the reservoir, and then you have a local pressure gradient down like that. So this is the producer, and this is the bottom flowing pressure of the producer, and this is the injection pressure, well injection, okay? Okay. And let's say that this P max is here. Okay? I'm just saying it could be anywhere, but let's say it's there. So everywhere in the reservoir, and if you look at volume, in probably 99+% of the reservoir, the way I've drawn it, because being radial wells, there's much smaller volume here than in here. So 99% of you have pressure in the reservoir greater than this maximum pressure. So pretty much everywhere, it's miscible first contact. Okay. You know, even if you raise the maximum pressure up to here, then you're still, you know, basically in this region here, it's not miscible. Or, you know, it's in this region here. So if it's below that pressure, then it's not going to be first contact miscible. Right? But even though it's not first contact miscible, the recovery efficiency will be very high near the producer, because the producer will see many, many pore volumes of gas flowing through it. So you basically want a good chunk of the reservoir at pressures above this minimum miscibility pressure to guarantee a miscible displacement.
So with the life of the reservoir, we continue to change this injection pressure so as to have pressure in the reservoir greater than?
Yeah, you know, that's a whole different. That's a little outside this. That's kind of like it's a production strategy. It's outside this. It's not in part of this course. So, but you know, where you control, you know, where you inject here will affect whether the average, you know, is above or below that. So it's kind of outside the scope of this course. Now, okay, so if there's not anything on your minds, then we've got some time left. So, I had one question I think that we need to think about. Is why or how does nature decide if a certain composition at a certain pressure and temperature is single phase or two or more phases? And I think it's important that we try to think through that. And the first thing is that nature always tries to minimize the system energy, if you will. Okay? And we've got these hundreds of components. We've got a total composition, a different distribution of all the components. We've got a pressure and temperature. And nature can decide to keep it as a single phase, and if it does, that single phase will have a certain energy. Okay? But if nature can come up with some other configuration where some of the methane is put into a lighter phase and some of the methane is put into the heavier phase, and likewise for every other component, if that configuration gives lower total energy, then Mother Nature is going there. Mother Nature won't tolerate single phase. Okay?
What would be your definition of the energy? Is it the pressure or?
Yeah, no. So that's what we're going to talk about. So we're trying. So what is the energy of the system? And I'm just going to kind of. We're looking right now at the chemical energies, and there's different forms of that. But the one I'm going to be talking about is, I think, the one according to the Gibbs chemical energy. And that total energy is well, let's just consider two cases. Case one is where we have single phase. And then the total energy will be equal to the total moles times the mole. Actually, I write it. Be the sum of the total moles of component I times the chemical energy of component I. And the chemical energy of component I can be calculated from the overall composition, pressure, and temperature. You also need the molar volume, but you can get that from the composition, pressure, and temperature. So there's an equation to get the chemical energy of methane, separate from ethane, separate from propane, and so forth. You just need the overall composition, the pressure and temperature, and you can get that from an equation. And then if you weigh the individual component energies with the amount of moles per component, then that's basically your total energy. And if it's single phase, then we can just take that outside and write mole fraction Zi for the, and I'm going to write it Zi for this composition Z. It's a function of Z, so I'll just write it that way. So in a sense, Mother Nature needs to calculate that first. Okay? Now, if you have two phases, then the total energy would be the number of moles in the vapor phase times the mole fraction of each component times the chemical energy in the vapor phase, plus, which is a function of Y, plus the moles in the liquid phase, composition, molar fraction of the liquid phase, times the energy of component I in the liquid phase, which is a function of X. In this case, we have the constraint that Mother Nature says that a component I needs to have the same level of happiness or energy if it's in the liquid phase or the vapor phase. So if Mary Jo is swimming around in the liquid phase and Mary Jo wants to jump up into the vapor phase, Mary Jo can do that without any gain or loss of happiness or energy, can jump up into the vapor phase. That's fine. But then Tomboy is going to have to jump down into the liquid phase to keep the balance of how much of is in each phase. Okay? But the energy of component I in the vapor has to be equal to the chemical energy of component I in the liquid. Okay? So that's kind of a constraint for the two-phase case. Now, the problem is there's so many combinations. There's so many combinations of the number of moles of vapor, moles of liquid, Y, I, and Xi, that it can be a very exhaustive search looking for this. So this, we're going to call this two-phase total energy, and this is total energy for single phase and two phase. So this is how you calculate for two phases. Now, if the total energy for one phase is less than the total energy for a two phase, where you've satisfied this, set of constraints, then it's going to be what? Single phase or two phase? If nature always wants to try to minimize the system energy, then if the single phase chemical energy is less than, then we'll have single phase, right? And if the two phase energy is less than the single phase, then it'll be two, and actually you don't know for sure, it might be more, but at least two phases will exist. At least two. And it's incredible because there's an infinite number of possibilities with xi, yi, and, well, not infinite, but there's a lot of combinations of xi, yi, the moles. You've got a certain number of moles, so you also have to know that total moles is equal to vapor moles. You've got that as another constraint. So you've got all these constraints you have to satisfy. And so it's a pretty heavy task looking for all of these, trying to find one case where you have less energy. Okay? So this fellow Gibbs, who kind of developed the whole theory of this phase equilibria formally, he said that, well...
Sorry. Does it mean that we have to find one case that where the two phase is less than...
If you find one case...
Or all of the cases have
No,
to?
you only have to find one case.
Okay.
You only have to find one case. But it has to satisfy the mole conservation and the equilibrium requirement. But what Gibbs gave is a simplified search, or a simplified method, only to identify if it's single phase, or to eventually plus phases. Okay? He gave a simplified way to do that. And what he said is that if I'm going to call this total energy star, which we're going to calculate in this way. We're going to calculate it as if we can just find one composition, which I'll just call UI. UI is just a composition. Any composition, sums to 1, times the chemical potential of that composition. And if you have epsilon of that composition, just an infinitesimal amount, plus 1 minus epsilon of the composition you know. That's the single phase energy. So if you can find any composition U where this is less than this, then it's guaranteed to be 2 or more phases, without telling you how much of each phase or what the 2 phases are. But it definitively tells you that there's at least 2 phases. So now all we have to do is we have to search for one set of compositions, not 2 sets in the amounts. And now I think the constraint is simply that this needs to be proportional with this. In other words, the ratio for all components is a constant. Okay? So the chemical energy of that new composition we found, it doesn't have to be equal to the chemical potential of the component in the original phase, but this ratio for all components has to be a constant value, 1.036, 0.9827, something like that. So this is a more efficient, simpler way to identify if it's single phase or two phase. It doesn't tell you how many moles are vapor, how many moles are liquid. It doesn't tell you what the compositions of the two phases are. It just says this is definitely not single phase. Okay. Now, you still have a challenge. I wouldn't call it a problem, but you have a challenge to look in a large composition space for this composition UI. I mean, is it 92% methane or is it 62% methane? I mean, there's a lot of different combinations of composition you can try. And how do you do that systematically and efficiently as an engineer who has to do the calculations? So there is a challenge in looking for that one case, and that all you need is one case, one composition that satisfies this, and then you're done knowing that it's single phase or two phase. You can make the map of this envelope of the phase envelope line. Okay. 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 I think that's pretty much it on all of the phase types of phase diagrams. That's covered. Next week, what we're going to start doing is talking about how to do the calculation of saturation pressure if you know the composition and temperature. So you can start actually calculating that phase diagram. That is covered in basically in chapter, I think, 3 is calculation of saturation pressure. Bubble point or dew point, and also the calculation of a two-phase flash, a two-phase equilibrium. We usually call that a flash. To find out from the composition at pressure and temperature how many moles of vapor do you have, how many moles of liquid you have, and what are the compositions of the two phases. I think chapter 4, maybe I need to kind of go through the book. Let's see here. See what's in chapter 3. Okay. So I think the only part of chapter 3 that you need to look at is the k-value correlations. That would be 3.6. So specifically 3.6 on k-values. Let's see. Yeah. And then chapter 4, in section 4.3, the two-phase flash calculation. And then probably 4, 3, and 4, 5. And anywhere it's talking about using the equation of state, you can ignore that. Okay? So, it's basically equations 474, 475. Is all you really need to you don't need to study all of the section because much of it's about the equation of state. And in section 4.3, um, four, 3, 1. Only. Okay. So in section 4.5, you only need to look at the equations 474, 475, and in section 4.3, it's only 4.3.1 section you need to study there, and then basically all of this section here. So if you want to prepare for next week, this is what you would need to look at.